for the recording purpose. So as I said, we are going to discuss about trees and different common types of trees and what is the tree notation, how the tree data structure can be defined, and what are the applications of tree data structure, like what are the different usage the tree data structure and the tree problems. So I did not even wrote like I will start writing different problems, algorithm problems, but we will discuss the basics today. So and then we'll start covering in the next couple of sessions. So as I said, tree is a very popular data structure, very useful for many of the applications in that regular daily usage applications and apps right now, like Uber or Google Directions or Maps. Flight searching. So many applications are built, with this data structure because of the flexibility of the trees and graphs. Especially the graphs is so, have more, usages in those kind of algorithms and applications. So like searching flight searching different flight options between different destinations, or finding nearest restaurants, or finding nearest drivers in the Uber app. Those are all the different graph algorithms. Or shortest distance. What is the shortest way to from one place to another. All those happens within fraction of seconds, milliseconds, because of these great data structures. So especially the graphs. So before we entering into the graphs, trees is a kind of basics. We need to understand how the trees work and what are the different trees algorithms, and then that will enable to understand the graphs. That's why I started with trees. Let's look at different types of trees and notations, and if we still have some time, we will look at the traversal. I think I'm hoping you guys remember these kind of names, at least in order, pre-order, post-order. So it's a very popular, algorithm names when we studied our data structures in our MS. So we'll start with that, the basic algorithm. What are the different traversals, and then go through the other algorithms and going on. So yeah. So what are the trees? So let me use the whiteboarding for easy explanation. Okay, can you guys see my inking slate here? Right. So
Yes.
as we know, yeah. So the linked list, as we know, linked list has links from one node to another node. Right. Every node has two things, mainly the two things. One is the data, and the other one is the address or the link to the next node. What is the address in the memory? So as we discussed from the beginning, arrays, the main thing is they are contiguously or continuously assigned in the memory. But in case of linked list, we know these elements can somewhere in the memory, in the RAM. So we don't know it necessarily. They may not be in a single or contiguous memory. So that's why we are storing the address here. So the main advantage is like limitless. You can create millions. If your memory supports, you can create multi-million nodes, and you can link them, right? So the same thing with trees also have the similar kind of concepts, like a data and also the address of the next nodes. But the main difference here is sequential in terms of linking. That means in order to go to the different nodes, you need to start from the head. This is head node, and you always go either in two directions. If it is single linked list, only go to the next node. If it is double linked list, you can go to the next node, and you can also traverse back from any node, back and forth, right? So these are the only two kind of ways of doing it, traversal. So the main difference between the linked list and the trees is hierarchical. So it's a hierarchical kind of representation. So if you have something like in a linked list, you cannot represent in a hierarchical way. Let's say it's a family tree. So if you want to show that kind of thing, it's not possible with the linked list, right? Whereas in case of trees, you can make it happen. So that kind of hierarchical data If you have hierarchical data, that's better is used to go with the trees. So trees always has a kind of root node. So in case of linked list we call head, but in case of trees we call it root node. So this is root node, and the root node can have multiple childrens. So that's the main thing right here. Sometimes like tree is like the main difference here is in the linker list at max either only one address, right? If you are looking for single linker list, only two things: data and address. This is data and this is address. Only two things. Only one link which can go to the next node. But in case of double linker list, only two things, right? So we have a previous node and we have next node, and this is the data. So only two at a max. But in case of trees, if you look at the normal tree, it can have n number of children, right? If you look at normal tree itself, if you look at the branches and root and branches and then leaves, there is no limit for the leaves. It can a branch can have n number of leaves. So even this particular branch has another kind of n number of leaves, right? So if you look at in terms of that way, this is hierarchical and limitless kind of addresses. So how can we store this? It's important, right? So just imagine if you are thinking in the same way. Let's say this is a node, exact same representation as we have single linked list. This is a node, okay, and node has a data. It could be string data or integer data, whatever the data you want to store. You can store, if let's say if you want to store an employee object, all the employee, let's say if you want to store the organization tree, the top of the tree is CEO, and after that you will have board members or the CFO or whatever the next people after CEO will be here, and then other managers will be here. So now you want to store that whole data, CEO object here, the employee object which has all the things like name, title, designation, all those things. You can store that whole data here. Now we don't know, well, how can we store this data structure in such a way which can provide three nodes or five nodes or 10 nodes. In If you look at the really big company, in under CEO there will be 10 people who is reporting to CEO. If you look at the small company, maybe just two or three people who reports to CEO. So how many addresses you're going to create here? You are creating software that should work for both a small company and also it should work for Microsoft, let's say. So how can you define this node in that situation? So what is the best way? So because if you are saying, like, if you are creating a node with the data and three, let's say three nodes, like leaf 1 L1, like L1 L2 L3, leaf 1 leaf 2 leaf 3. So it will only support three children. If you are installing your software with a company where CEO has around 10 people under him, you cannot even create that object, right? Because you need to have 10 addresses here. But here they only, if you are supporting only three children, right? So how can we define that? So how it's like, it's a dynamic thing, right? It could be like three addresses, or this node can go to three addresses or four addresses or 10, right? So what is the best way to define that? So there is a data structure. I think I did not cover it. I don't know whether you might definitely know it. There is a data structure which is like a dynamic assignment. If array, if you want, it's the one thing you can put the addresses in an array. But if you want to put it in all these addresses in an array, the main problem here is you need to define what is the size. What is the size of the array you want to maintain? You don't want to allocate unnecessarily like a, okay, I will take 100. Unnecessarily 100 allocations will happen for each node, but only three or four people for the CEO. So there is no value of putting 100, right? So there is another data structure which is dynamic allocation. Any idea? So
No.
this node should be able to have either one node, like this node has three addresses and this node has zero addresses. This node has four, right? This manager manages four people here. So this particular node has four addresses in this list. I was told, actually, what is the best algorithm or the best data structure to store the arbitrary number of next nodes. Any idea? Array is not going to work. Another
There's
thing
something called
called array
map.
list. Exactly. Map is, yeah, exactly. Map means it shouldn't have the key value pairs, right? Is it? I'm still confused. I think map has just a list of values where you can add more, right? Dictionary has key value pairs, correct?
Map has a key
Yeah.
value. Map is also key value, sir.
There
I
is one
think.
data structure which just where you, because there is no key value here, only values. You just need, here is the CEO data, and here is the address of this rest of the people under CEO. So you just need to store the address, right? Just like our previous node and next node which we discussed last week. We don't have a key for each of these, just address. This is the address, this is the address. So in C sharp it is called array list. I don't know what we call in Java, or like array list is something like dynamically you can keep on adding, I think. You can add n number of elements into the array list. What is the equivalent name in Java? I think,
It's also array list. We have array list.
yeah, array list in Java, exactly. And I don't know the actual name in another languages, but that's the same thing. Like array list provides n number of elements, so you can add 10 elements or 20 elements. It doesn't matter. Right? So you can keep on adding. So that's the main thing. So part of collection framework and is presented in Java. It's there actually. Yeah.
పడిపోతుంది ల్యాప్టాప్ పడిపోతుంది అలర్జీ కూడా చూస్తున్నారు వీళ్ళు. అవే.
See, this is the main thing. As I said, the array list is a resizable array, which is represented in Java, while built-in arrays have fixed size. Array list can change their size dynamically. Elements can be added and removed from array list whenever there is a need, helping the user with memory management. See, this is the main advantage of array list. So when you are building something which is like a unknown number of children, right? We don't know this particular, as I said before, this particular node has 3 or 4, and this particular node has 10 elements. So if we have a really big team, let's say he is the manager, he is managing around 50 people. So this particular guy has a 50 children's, right, child nodes. So the array list is the best representation of this whole node, where you have a data and in the array list of next nodes. If it is 50, you will have all the 50 in this array list, because so you can iterate them again. So if you want to see the names of all the people under this manager, what you do is just iterate the for loop and array list. Just write a for loop, and you can get the names of each person, or the salaries, or whatever contact numbers of each person under him, right? They are equal. There is no link from this guy to this guy, right? He is not managing this guy, he is not managing. So it's not a good idea to use linked list. If you are using a linked list, we are creating unnecessary problem of linking these two guys and linking all these people. We don't want to link them, because the link represents there is a reporting, let's say reporting structure. So there is no link from this guy to this guy. These are peers, right? So in that situation, there's some data structure which stores the elements separately without any, links between them, is the best way to represent. That's what the array list. So that's how the normal data structure, this normal tree, any tree can have, n number of children, right? That is the tree. Now let's say an example. If you want to give an example, like very simple example, A and B, C, D, and this can have H, let's say I, J. It doesn't matter, right? Whatever the data. So now, so it's just a tree like this, right? So now there are different traversals for the trees. We can discuss those, or we can also discuss about the different binary different trees. Okay, let me just give a few hints about the traversals. So one simple traversal, as we discussed, is hierarchical traversal, right? So you want to know at this level, this is a higher level, how many people, and the next level, how many people in this company. Let's say this is an employee structure. So on the CEO, always the root is always one, and then you will see the next structure has 3 people here. So what are those three people under CEO? That means you're navigating A, you're printing. Let's say you want to print the people in a hierarchical way. So you want to A here, and then you want to print the people in the next level, B, C, D, and now who are the people in the next level? There are no people under B, under C, right? These are just employees. Let's say those are the assistants of CEO. So they don't maintain their own. There is no team for them. But D is a manager who has three people, and these three people. So when you are displaying, let's always go with the kind of direction from left to right. Let's say A, B, C, D, and then H, I, J. So this is called hierarchical printing, or the breadth first search. This is one of the actually algorithms. Breadth first search. Basically, you are searching for an employee by using a breadth first. Breadthing, like breadth means like the width of the whole tree, right? You are navigating the whole breadth of the each level. Let's say this A has 1,000, or let's say 100 people under A. You are navigating all those 100 people and finding some guy. You want to find a guy called X. You need to know where the X is. So you can go through level by level. You check whether A is X. No, you check all the people under him. It could be three, or it could be 10, it could be 1,000. You will go in a breadth wise and check whether X is did you find X? No. If you did not find, let's go to the next level. What are the people of B? What are the people of C? Let's say B has K and X here, right? So let's say then after A, B, C, D, right? You don't go to H yet. So it will go to the K and then X, and then you stop there. You found X. Let's say if you are looking for J, then you go again. After X, you go for H, you go for I, and then J. You found J finally. So this is called breadth first search. So this is one of the traversal, and this applies to the any trees. It could be trees, binary tree, or the normal tree. I will explain what is binary tree right now. So is it clear to any everybody, or any questions so far?
It's clear.
Okay. Okay. Great. Yeah, so that we just covered the trees, the tree, what is the basic tree, and then notation. We covered the notation in terms of just diagram. I will show you in the C# code as well how to define the tree. And coming to the binary trees. So, what is the main difference between tree and binary tree? Anyone can explain? Can can anyone attempt to answer that based on the memory you have from your class, couple of years ago?
Binary tree has
Vanilla
two.
or yeah, Shivagaru, yeah, Shiva, can
Uh,
you attempt like what is the
yeah,
difference?
sure, sure. And I think someone was trying to answer it, but it will have only two, at most two childs only. So you can
Exactly,
have zero, one,
exactly.
or two, not more than two. One left and one right.
That's exactly, that's a perfect definition. Yeah, thank you, Cicely and Shivagaru. Yeah, so yeah, this is basically binary tree is a little different. Only thing is, as we are saying, binary means so two, right? Like either max two. So if you consider this tree is not a binary tree because A has three nodes, three children, and D has three children, so it won't satisfy the definition of binary tree. So let's go ahead and look at the binary tree. So binary tree is something like this: A has, let's say, B here and C here, and then B has, as he said, it could max two elements: A, B, C, let's say D, E, right? And let's say C has K, so it's still a binary tree. And let's say K has L, let's say this is still also binary tree because A has two childrens, and B has also two childrens, D and E, and C has one children. C doesn't have a right node. That's okay. It's like either 0 or 1, 0, 1, or 2. Any node should contain either 0 children, 1 children, or max 2 children, right? So K does not have a left children, but K has right children. So K also, this whole L has zero children, D zero children, E zero, children. So it's still binary tree. It satisfies the condition of binary tree. So it is a binary tree. So why we need binary tree? It's like various advantages probably in binary tree, and a lot of what we call applications of binary trees. So I forgot to say something. Yeah, so this binary tree is yeah. Now let's look at the notation. So as we just discussed before, so every node is just we need to create a class, right? One is data. As I said, we will store, which could be string data, it could be integer. We'll store the data here. Now addresses. Now we know the definition of binary tree. Is it still possible, or is it still necessary to use the array list to store the addresses of the children? Is it still useful to use the array list, or is there any other alternatives to store the children? Can anyone answer that? Cecilia. So do you think it's necessary to use the array list?
Um, I think so. I'm not sure.
Yeah, you
I
can
mean, you
store the
still
array list.
need. Sorry.
Yeah, but yeah, go ahead.
Sorry, I was just saying that don't you still need the addresses of the children node?
Yeah, we still need the address of the other children. Array
Mm.
list is perfectly fine to use this, but array list, why we use array list last time is to store arbitrary number of children, right? It could be the
Mm.
one A has children, A can have 100 children. We don't know how many children A can have. At the same time, B, we don't know how many child nodes B can have. So that's why we used array list, because it facilitates either you can have zero children or one children, two or 10, 100. So it's an arbitrary number of child nodes we can maintain. But here we already know there is, for if you're looking for the, if you are creating a binary tree data structure, we already know this. At max you will have either 0, 1, 2, right? So there is no, if you are creating a binary tree, according to the architecture and the software, so you no need to you should not store more than 2, right? So in that situation, you already know max is 2. So would it be easy to use the other simple mechanism? Just why we use array list to have this whole thing? We know it's max 2, right? There are two options. Either you can simply take an array here, just take an array with two values, right? One is like address of the first children, left children, and the second one is address of the right children. Very simple, just array of two elements, because we always know it's just max two, right? Or the main problem with arrays, again, you need to navigate like a zero, like zeroth element, first element, last element. So instead, why can't we have two simple two addresses? Just like our double list, right? Double linked list has something like previous, next, correct? So here is the data, and we can simply call left node and right node, let's say ln and rn, simple like that. So this left node, so this pointer points to the left node, and this pointer right node points to the right children. Left or right, you can have L, just L or R, or left children LF, or right children, RF, something like that, RC kind of, children. So so would that be easy, right? Would you agree on that?
Yes.
Yeah, because it's always either zero. Zero means like there are no children, simply both the pointers will be null. If it is one children, if it is let's say left children, then the value will be here. There is an address for left, but the right is null. If you have right, right will have address and left will be null. If you have both children, you will have those, both will not be null. So you will be able to navigate. If you want to go to left children, you can use left children, left node, and if you want to use right children, you can use right node. So is it clear, Shiva and Vinila? I think you dropped and rejoined.
Right? Yeah, it's clear. It's clear.
Yes, Suresh, I dropped again.
Yeah, so basically what I'm saying is no need to use the array list in this situation because we know the max number of elements is 2. Simply by having two variables left and right, simply L and R, left and right has a way to navigate to the children, right? That's the notation of the binary tree. And what is a binary search tree? Can anyone attempt on that? Binary search tree. This is we just added a word called search. Binary search tree. So anyone have any idea, or do you want me to go ahead and explain? Okay, I will go through that. So basically, binary search tree is a binary tree with an additional condition. So we already know the condition of binary tree, right? Binary tree is either 0, 1, 2. Binary search tree has additional conditions on top of it. So mostly the binary search tree is a comparison with the elements, like a comparison of this and this, right? So um, I would say it's better to use numbers to represent the binary search tree because you cannot, like, what is the comparison between A and C? Like it's data structure right now. It's just the integers or the characters. If you cannot compare A greater than C, C greater than A. Of course, if you look at the ANSI numbers, ANSI representation, you can find which is greater than which is less than. But in a simple way, if we use the integers, we can represent the binary search tree. So the main condition here is that in binary search tree, basically, um, the value, I did not remember exact definition, but I will tell in my own words. So the value at the right children, it should be greater than or less than, no, sorry, it should be greater than the left node, greater than or equal to left node, and value at the right child should also greater than the right node, or the root node, sorry. So something like this. Let's go with an example. Let's say 10 here. If you are putting 10 here, now, as you know, it has either 0 or 2 children, right? Now someone asks you to, okay, we store 10, please store 8. If someone says store number 8, you need to store number 8 on the left side because 8 is less than 10, right? The left nodes are always lesser than the root node, and the right nodes are greater than the root node. So let's say someone say add 15, right? 15 should be added in this way. It should be like here, 15 is here, right? So this is a binary search tree. If you go in this location from left to root to right, you will see an increasing order. That means 8, 10, 15, right? So that's the increasing order, right? So is it clear?
So we need to only take only the numeric, right? In this case.
Exactly. In most of the binary search algorithms or numeric algorithms, even though like you can think of this way, we have ABCD, CEO, 100 people. Now you want to store all those people in this order, right? Let's say a company with 3 employees. Okay, CEO A, you know, has a 15 million as his salary. Let's say now B is a 10 million salaries, and now C is 8. So in a normal binary tree, in a normal tree, what we did is we something like this, right? We added something like this. A manages B and C. Okay, because A is CEO and B and C are the the people under him. We will have something like this. Now A salary is 15 and B is 10, right? And C is 8. Now this is a binary tree, but it is not. Is it satisfying the condition of the binary tree? No, right? Because this is okay. 10 is greater than, 10 is less than 15. This particular, if you look at these two, if you look at these two nodes, it is satisfying the rule of the binary search tree. Binary search tree says the left node should be less than the top. Yeah, the B salary is like 10 and A salary is 15, which is good. But now let's look at the other side. A is 8, C is 8, and A is 15. So it's not satisfying, right? This is not satisfying the binary condition because all the right nodes should have greater than the root. So now 8 is greater than 15? No, right? So now the representing this way is not satisfying the binary search tree rules. So the same people, even though you're thinking as an integers, let's say I'm saying like represent these three nodes using their salaries in a binary search way, in a binary search tree. Now in that situation, what happens? Where can anyone tell who will be here and who will be here and who will be here? Who will be on the top? A, B, C.
10.
B.
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 Exactly, exactly. So B will be here. Okay. Now who will be on the right node?
So
I think A.
the right node will be A.
Yeah. And who will be on the left node?
C.
Meaning C. Yeah. Now the same people. See, it's not representing. Now if you look at, this is a BST, binary search tree. This is a representation of binary search tree, representation of the organization, but it's not representing the reporting structure. Don't look that B is managing E and C. This is not a this is not this reporting structure of the managers and the subordinates. That is the normal structure here. If you want that structure, don't create BST. Okay, the same people, same employees, you will have in one software, in one class you can have the normal tree like this. A manages B and C. In another class you can have the BST because it has its own advantages of maintaining this way, right? If you want a normal hierarchical structure, go with this class, go with this tree. And if you want to do something else with this, I will tell you what is something else with BST. If you want to do searching, and there are a lot of BST applications. So though if you want to do those kind of algorithms, it is best to go with BST. So this doesn't represent the the hierarchical structure inside the organization or inside, but it represents the BST format. So B still have 10 and A is 15 and C is 8. So it's satisfying the condition, right? So all the left nodes are greater than the B, the root, and the right nodes are the greater than root node. So this is left node, this is root node, and this is right node. So this is root. So this is the BST definition. Now, since we are in this diagram, before going to the next one, I will ask you a question here. Now, these guys, three people are in this organization. This is so now the organization is becoming big. They want to recruit new people. They recruited a new guy who is D. They want to give a salary of 12 million or 12,000, whatever you can think of 12. So now I want to represent. Now he's reporting. Let's say he's reporting to. He's reporting to. Even though he is earning like B is earning 10 because he is coming from, let's say he's coming, D came from Microsoft. Let's say we want to give 12, but he reports to B. So how do you put in the normal organization? We'll put here, right? This is the D place because A managing B and C, and now B is, even though B is earning just 10,000, D is earning 12,000. So,
Another
but he is
department.
under B, right? So D is under B. Now, can you tell how to represent in this BST format? Where do you want to put D?
It will be
So
under
we already
15.
have something like, okay,
Uh,
we have, let's
yeah,
see,
right now.
let's see,
It will be under 15 in the
let's see.
left node, right?
Oh,
Uh-huh. So in the current BST, we have B is on the top, right? And A is here. Okay. Can you guys hear me now?
Yeah.
Okay,
yes.
okay. I think I got muted. Yeah, no problem. Okay. So now we got B with 10,000 and A with 15,000, E and 8. So now here we have something like this. Let's look at in a normal way. Let's don't confuse ourselves with the A, B, C, D. So let's look at in a normal way. So now we have 10 here and 8 here and 15 here. So now we want to put 12. Okay, we start from the root, and as I said, if the 12 is it if the number is bigger, it should go to the right side, because that's the rule, right? If you want to put 12, you should not put 12 the left of this node. 10 is at the root, right? So as I said, the numbers greater than root node should go to the right side, right subtree. So now now 15 is here. Where do you want to go now? Because 12 is less than 15, right? So now 12 will become the left of 15.
Left of
Is
15.
it clear? Because it follows the same BST rule. Because you want to insert 12. 12 is it greater than 15 or less than 15? We will check that. If it is less than, go and add to the left node. If it is like, let's say if you are adding a D with 18,000, let's say 18,000 means it has to go to the right side. So since 12 is less than 15, so it has to go to the left side. There is no children right now 15 is just a normal empty. He is not managing any people, so now we will just put under, you know 15. There is, if you are still have some other number, right? So let's say if you still have a 13 or 14 something here, again you need to decide, should I go left of 13 or right of 13? Those are the conditions you need to verify at every point before you placing the children at the right place, before you adding at the right place. So inserting in the normal tree is very easy. It's very easy. Tell me who is a manager, I will just assign to him. Simple. Let's say A is managing already B and C. If you say D, if you want to put D under A, no, you said nope, sorry. It's a binary tree. This is binary tree, BT. Binary tree, it has to max two nodes, right? A cannot manage D because A already have two people, B and C. You simply say we cannot add as a subordinate under A. Simple. But if they say add under B or C, we can add it because B and C are not managing any people. We will simply add. If you want me to add under B, we'll add here. Simply, if you want to add under C, we can add. In a normal binary tree, it's easy to add. But if it is binary search tree, you need to decide the correct location before adding that people. So now if you look at this, right? Or is it, am I muted again? Oh, can you hear me?
Yeah.
Yeah, we can hear you. Hear you, sir.
Okay, sorry. I just want to make sure. So now it is clear, right? So when we are adding the numbers, we need to find out the correct location. Now, if you look at the numbers here, B is still at the top in the BST, C is here, and A is here. Now the D look likes under A, but look at this. As I said, the you added D under A, but it's not like A is a manager of D. As I said, this BST doesn't represent um, the 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 um, the management structure or the reporting structure. So it represents the sequential or the increasing order from left to root, root to right. So now if you, that is called in, I think it is in order. If I did not mistaken, I think that's in order. In order traversal is always like that. Let me just double check before going, before confirming. So in order always has left, uh what is that, n, oh, root, oh, left to right node. Okay, in order is always like that, I think. We can check it here. So tree traversal is always little confusing, but I want to double check before telling. It's already loaded here. Okay, see this. So this is a binary search tree. In order is left, root, right. So 4, 2, 5, 1, 3. This is a binary search tree. Do you think it's a binary search tree? Yes or no?
Yes, it has a max of two nodes.
No.
Binary tree. This is a binary tree, but I said is it binary search tree? There's a
Binary search
difference
tree.
between binary tree and binary. Is it a binary search tree?
No end, because I see 4 is there, 5 is there, 4 is greater than 2, so it should come to the right, but it
Yep,
is on the left. That's why it's
exactly.
not right.
Exactly. So only there is one and three. One and three are satisfying the condition of binary search tree, right? Because one is smaller
Okay.
and three is greater. But binary, that's the condition I said, right? Binary search tree is always like this. The root node should be lesser than all the nodes on the right side. Again, the same thing. All the left side node should be lesser than the root node. So if you go from this way, you will have a increasing order, ascending order. That means in order. So let me double check that. That's what the in order is. If you look at in order here, right? So left, root, in order, left, root, right. That's what in order. So left, this is left, and this is root, and this is right. If you go in order traversal, will have all the numbers in a increasing order. Let's say you want to put a simple application in this organization is, hey, I want to list the employees in the order of their salary. Don't say like A, B, C, D, because A, B, C, D is giving like 15, 15, 10, 8, and 12. So 15, 10, 8, and 12 is not an increasing order, right? So you are starting from a CEO, and I don't want the list this way. I want a list with employees which are having this increasing order. So if you, the one way is like you can put all these numbers in an array and sort it, but there is a way. We don't want to put another array, and we don't want to copy all these elements in the array and do the another big sorting algorithm. It will take a lot of time. So there is another way where you can use binary search tree. If you have binary search tree, it will provide this in order traversal that will give you this great flexibility. So now let's look at the in-order traversal of this. In-order traversal means you start with the leftmost node. Always starts with the leftmost node of the tree. So that means even though you are at the root node, we always have access to the root node. We don't know who is at C, who is at the last in any tree, either in the binary search tree or binary tree. We always have access to the root node. But even though you have root node, you don't print the root node. We know that he have a greater salary than his left children, right? Since you need an ascending order, don't print 10. Go to the left node and see, do you still have any people under 8? No, 8 is the only guy who has a left node. So if you go left node, there is no left node, there is no right nodes. So simply print 8. Now go back, because there is no children. That's the thing. Left and then root. Go to the root and let's print the root 8, 10. Now go to the right subtree. Now again, if you visit 15, don't print 15 yet, because the problem here is there could be some people who are getting lesser salary than 15, and those people will be on the left subtree of 15. So whenever you are touching a node, don't just print that immediately. Just check, do we have any people who is drawing less than this guy's salary? Yes. If you go to the left node, you will easily find it, because that's how we design the BST, right? So you don't need to do any comparison. If you just simply say, does this node has left node? Yes. Go there and again, once you go to the 12, don't print 12 immediately. You just check again, do we have any person who is drawing less than 12? That means, let's say the 11,000 people. Let's say at some point tomorrow, next week, another guy joined with 11,000, so he will be left of 12, right? See that you cannot put 11 at any point here, and 10 is here. You should go here, and you cannot put 11 to the right of 15, because 11 is greater than less than 15. You will go here, and 12 is here, and then you should put the 11 at the left of 15, left of 12, right? So that's why before printing 12, you will check again, do we have any left node, do we have any right node? Let's say another guy joined with 13,000 or 14,000, they will go to the right of 12, correct? Because they are less than 15 but greater than 12, so they will go to the right of 12. So you will need to check all those people. Do we have any people with 11,000, or do we have any people with 13,000 or 14,000 salaries? No. Now we are good. Let's print 12 and then go back to the root. Now we know that we already completed left side. Now we confidently know that 15 is the next guy. After 15, you don't stop. Let's see if you have any right nodes. Do we have any people who is drawing greater than 15? Let's say you have a CEO. Now you want to assign some board of director who is, let's say, just putting some example, or another CEO or another person who is greater than the A, and who is drawing greater than the salary of A. Let's say 17,000. Let's say that guy, we need to print that guy, right? So that's why we will check, do we have any right nodes? No, we don't have any right nodes right now. We are good. So that's the ascending order of the employees in their salaries, in terms of their salaries. So in this way, you will print C, B, D, A. This is the actual order of employees based on their salaries. Correct? Is it clear? This is called in-order traversal. Actually, I thought of explaining other types of trees, but I already jumped here all the way to the in order algorithm.
Yeah.
So yeah,
Clear.
any questions so far?
It's clear
It's
now.
clear.
Is it clear?
It's clear.
Yeah, that's great. That's great. That's great. Yeah. So binary, this is the main difference between normal binary tree and binary search tree. It always satisfies this condition. If you are storing without satisfying this condition, that means it will create problems in the future, right? If you are putting anything like, let's say, if you are putting 14 here in place of 12, if you are putting 17 here, you know you will not be able to print in this ascending order, right? Because it will say 8, 10, 17, and 15. So whenever we are adding, if you're adding elements to the binary search tree, it should satisfy this condition. At the same time, removal is also another big algorithm. Let's say the guy with 15 resigned. Now he said, I'm not the CEO of this company, I'm going to another company. Now there are a lot of ways, like either you can make B is like 10,000, or you can make D, in place of 15. Simple, right? So since B is, anymore, the A is not there, so you can move the 12 in the place of 15. You can move 12 up. You can do that way. So there are different ways to rebalance. That is called rebalancing the binary search tree. Basically, we need to balance the tree. When you are deleting, when you are adding, we need to make sure the proper element is deleted, and the remaining elements should be connected properly. Otherwise they will left out. If, let's say, 15 has another element here, if you are just removing it from 10, you cannot navigate to 12 or 17 here. You need to change those links appropriately, so that you will be able to navigate rest of the nodes in the tree. So those are all really good algorithms. removal of elements, adding of the elements, and rebalancing is different. I misspoke. The rebalancing is different. The rebalancing itself is another big algorithm. So I will, if you have time, I will practice and explain you later. That's all about the BST and BT, binary tree and binary search tree. We still have other in traversals. We can also do that. The traversal is basically, if you look at here, this is in-order traversal. So these traversals can apply to any tree. It doesn't matter whether it is binary tree. No. I'm wrong. So it will apply to binary tree and binary search tree, because if it is normal tree with 10 children or 20 children, it doesn't apply. Um, yeah, it's only like left and right. If you look at the and definition itself like this: left, root, right. At any point, so you have only two nodes. So this traversal applies to all these three traversals applies to both binary tree and binary search tree. So this is in order, and pre-order is basically, pre-order means root left right. So if you look at this pre-order, root left right, see the 1 2 4 5 3. So root is like, 1 is root, you visited a 1, and then you go back to 2, right? And then root is completed. Let's go to the next left, 4. So you completed root left, and then you have to go to the 5. That's number 5 here, right? So that's why 1 2 4 5. So now you completed the whole subtree. Now you go back to the root 1, and then what is the right? 3. So is it clear to everybody? This pre-order is also this is slightly different definition than in order. In order starts with left node. It started with 4, but in case of pre-order, it started with root. But it's not like hierarchical. Don't confuse with the hierarchical definition. Hierarchical means the breadth first order or level order traversal. Look at this. This is 1 2 3 4 5. 1 means first level, 2 3 means second level, 4 5 is the third level. That is different than this pre-order. Pre-order means like, you are taking a tree, just a root left right, and printing in this order: root left right. So you started with 1, and then when you go to the 2, you just need to consider 2 4 5 as a small tree. Now you just 2 and print 4 and 5. Now you are done with the whole left side of 1. Now go to the right side of 1. The 3 might have different subtrees. Again, we will do the same thing. Since there is no elements for the 3, we printed 3 and then stopped. Let's say 3 has a left node 6. After 3, we'll get 6. So that's the pre-order. And the post order is a little different. The post order is like left, right, root. So now we need to go all the way to the left, which is like 4, and then we need to go to the right. We should not print a root. So after 4, it has to go to the 5 and then root. 4 5 2. Now you completed the left subtree. Now go to the right subtree. So that's 3. And you completed left subtree and right subtree, and then print the root 1. So that's why it's a 4 5 2 3 1. Is it clear? Am I going really fast, or I just want to hear some feedback?
No, it's clear.
But
Yeah.
how we can define these in order pre-order in the scenarios?
Yeah, defining, this is the definitions. As I said, like, if you want to print, this is the way to, uh, definition of in order. If you say, give me the in order traversal, this is the output we need to put. So we need
Okay.
to write an algorithm that should be able to navigate or print this way. So it's already around 9:53. I have the algorithm here, but if you want, I can show. But maybe if you want me to show next time also, I can show. So the main thing here is, for navigations, this is like, recursion is very important. So much use of recursion in tree problems. So I hope every one of you has full knowledge on the recursion. You know that, right? Recursion is basically calling the same method, right, from the same method. So inside the method, you call the same method. So it will use stacks underlying, right? So if you use recursion, the compiler will use stack under the hood. So so recursion is the way to print these traversals. So what I will do is I we have few minutes. I what I can do is I can explain these algorithms in detail in the next week. So we have program and everything is ready. So what I do is we have other things also. This will also we'll discuss next week. What is the heap tree? What is a B tree? B plus trees? Even I don't remember fully. Like I need to refer myself, like I forgot the definition of these, and we may not need to go that far yet. There is a try. Try is another kind of tree. Very interesting. This is used for dictionaries and finding words. If you are searching Control F or something, right? So I think try is a very interesting data structure. But anyway, I need to refer myself to explain this. And heap is another very interesting data structure. A lot of problems on heap tree. So what I do is let's stop at discussing the applications of data structures for now, and then we'll come back to the different notations and algorithms next week. So what are the applications? Why we need to discuss about the trees? So did I open that? Yeah, here is the nice page written by Geeks for Geeks. See why trees? Unlike arrays and linked list, which is linear data structures, tree is a hierarchical, non-linear data structure. That's what I said in the beginning, right? It's non-linear. It's not like one to the other and then next. So it's always like a hierarchical data structure. So one reason to use trees might be because you want to store information that naturally forms a hierarchy. Let's say file system. This is a good example, right? File system as a root node. If you go to the files like my computer, these are always in a hierarchical way, right? Root node and home, and then you know you will have course. Like you will have all the folders, different folders. So if we organize keys in the form of tree with some ordering like BST, we can search for a given key in a moderate time, quicker than linked list and slower than arrays. Oh, it's like they said slower than arrays. Interesting. So so we have different trees like self-balancing search trees, AVL trees, red block trees. Guarantees upper bound of login for a search. So the searching is really easy, and this is very interesting. Like that's where a lot of search algorithms in trees. So that is the main advantage. If you want to store something like keys, if you we all use database, right? SQL server or different types of SQL databases. Every database has primary key, foreign key. Those are all stored in a trees. That's why if you are querying a database, where can, let's say, select star from employees where employee age is greater than 45, within fraction of seconds you will get all those results. How it's possible? If you have employees of million employees, or like 10,000 employees, like how it's possible to search all the employees and compare their age and greater than 45? How it's possible within fraction of seconds without navigating all the employees? So if you use trees, if you use binary search trees, it will neglect the rest of the employees. It will always start with a particular location, and it knows where to go, right? BST has this capability, right? So those are the main advantages. It will go right or left, and it will take proper decisions at very quick, and it will give you the results faster than sequential search. If you are putting in an array, there is no option. You have to go through each element and see what is the age. If you are putting all those employees in a linked list, there is no option. You have to start from root, from the head, and you need to go on each and every node until all the nodes are completed, and figuring out who are the qualified results to put it on the screen, right? So that's the main problem with the normal sequential search. So here is another thing. We can insert delete keys in moderate time. That is also another interesting thing. So if you want to insert an employee in a very, very big linked list, it's a lot of time consuming thing. You need to navigate and then find out the location and then process the links. So we are unnecessarily navigating all them, all the elements. That's the problem with linked list. So quicker than arrays and slower than unsorted linked list. That's another thing. If the linked list is sorted, of course it could be easier, but if it is unsorted, it will take a lot of time to figure out the correct location. So yeah. And like linked list and unlike arrays, pointer implementation of trees don't have upper limit or the number of nodes on the link using pointers. It's exactly like that, right? So linked list also use pointers, and we can use a link from left and right, right? So other applications, so store hierarchical data like folder structure is exactly what I just said, right? XML, HTML data. Binary search trees is a trees that allows fast searching, insert, delete, and sorted data. It also finding closest items. And heap is a tree that data structure which is implemented using arrays and used to implement priority queues. This is very interesting. I will go through the next time. And B plus trees, they used to implement indexing in databases. As I said, this indexing and in sequence server anyways, that's always with this B trees. And syntax trees used in compilers. If someone is building a compiler, they definitely use these syntax trees. And KD trees, I don't know about this. And yeah, there is a try used to implement the dictionaries with prefix lookup. So this is another interesting topic. Suffix trees, spanning trees, shortest path trees used to routers and bridges, respectively, in computer networks. If you are looking at the networks, right, the Comcast and all these networks, they use these kind of data structures to figure out all the networks, inside it. So as workflows for composing digital images for visual effects. If you know about this, the using visual effects also uses the trees. So I think Cicely, you are working on a 3D company, right? So definitely your company might be using a lot of trees and these kind of data structures. So there are a lot of applications, real-time applications of the trees. So this is always good to learn. This is fascinating subject. So that's interesting topic as well. So cool. Yeah, that's where I stop. I think exactly at 10 o'clock. So let me know if any questions or is it helpful so far? Please give some feedback. Yeah.
So there's a lot of stuff available in trees. I just know the basic one, the tree hierarchy, but there are many things to
Yeah.
learn.
It's very
Exactly.
very useful and refreshing. We get all the concepts. It's like we're trying to recollect what we learned, and it's really helpful, Suresh. Thank you.
Exactly. Yeah, it's interesting as well. Yeah. Great. Thank you. Yeah, Cecilia, do you have any questions or are you also good or what you can say?
Yeah, I'm good. I don't have any questions at the moment. I had to review these topics, so
Yeah, sure, definitely. Go Geeks for Geeks is a really good site where you can, if you really have some time, you learn upfront. So, and I'm just giving a heads up, like if anyone wants to share their knowledge or their algorithm they prepared, always welcome. I will also become the student, and you take the lead and just explain the algorithm and show the stuff you learn. So it's kind of let's have mutual learning. So it's not always like I'm giving something and sharing. And so if you have some ready really good algorithm or topic you prepared, always please feel free to inform, and I will definitely give an opportunity so that anyone can present, right? So it's kind of mutual learning.
Sure, sure,
Cool.
Suresh.
Sure.
Thank you.
Yeah, it's great. Awesome. So yeah, have a nice rest of the week, and we'll meet again next week.
Thank you so much,
Awesome.
Suresh. Thank you all.
thank you.
Thank you all. Yeah. Bye.
Bye.
Bye.